In this video, I'm going over how you can tell apart principal-agent models from game theory models from models that are neither. So, and you could actually argue that principal-agent models are a subcategory of game theory, but I'm just going to separate those and make the version of game theory I'm talking about here a more symmetrical relationship between the two parties. You'll see what I mean. So when you look at a pair of models, and of course nothing is defined here, this is just two models, and of course you need actual definitions for these to make any sense whatsoever, but we can yet tell if they're principal agent or if they're game theory or if they're neither. So what is the definition here? So principal agent models are going to have a couple of characteristics. One is the principal's choice variable is going to be exogenous in the agent's problem. Alright, so let's check these two models. So we don't actually know which one is the principal and which one is the agent, but let's first test if this could be the principal. We have a choice variable s, and we see if that appears anywhere in the other party's problem, and it does actually. So the choice variable, the principal, is exogenous in the agent's problem, so it meets this criteria. The second criteria is that the solution to the agent's problem appears as part of the objective function for the principal. And let me show you what I mean by that. So what is the solution to this particular problem? Well, if you were to take the first order conditions, you would take the derivative, set it equal to 0, check the second order conditions and all of that. And what's going to pop out when you give that? Well, what's going to pop out is the optimal value of the choice variable p, optimal value, and that's going to be a function of every single exogenous variable in the whole problem. So it's a function of j in this problem, and actually k and p are exogenous here. Sorry, no, k and p. K and p are not exogenous. P is the choice variable, so those are endogenous. And q. So we have actually three exogenous variables, j, s, and q. So p star, the optimal p, is a function of j, s, and q. And that also means, of course, that you could write that without listing any of those. So p star is a function of s, is going to be one way of writing that. And as a matter of fact, this appears in the principal's problem up here as part of the objective function, so that we see that the principal is going to choose s in order to influence the choice that the agent makes for their optimal p. And that's going to optimize some part of the principal's objective function. And so there we have it. This is a principal-agent problem because it meets those two criteria. Now let's look at another example. Alright, so we have another model here, and we're going to check if it's principal-agent first. So we see, first we'll check, is this the principal, in which case we know that the principal's choice variable should appear as an exogenous variable in the agent's problem. Let's check if that's true. And we have the principal's choice variable, or this player's choice variable, is actually not exogenous in the agent's problem. So this is endogenous, so that is going to certainly violate the first criteria for principal agent. So that's not true, but let's check the other player, because maybe this is the principal and this is the agent. So let's see, does this choice variable r appear exogenous in the other player's problem? Let's check that. Well, r does appear in the other player's problem, but it's not exogenous. This is endogenous, so we've already violated one of the criteria of principal agent, so this is not a principal agent pairing. Now, maybe it's a game theory pairing, and so let's check for that. So game theory, what are the criteria for game theory? And I'm actually going to do Nash equilibrium here, so let me write that out. Okay, Nash equilibrium happens when each player's choice, of course that's going to be what's their choice of the choice variable, or what's their solution, the optimal choice of this. Each player's choice is a best response to the other player's choice. So to think about this, let's first think about what is the solution to these models in the way I just described. So If we look at this top model, we take the first order conditions, yada, yada, yada. We do a bunch of work, and that's going to generate the optimal value of D. And we remember that D star is different than D. This D is allowed to take on any value or any value within a restricted set. Therefore, we can draw graphs of it. This D is one specific value of D. And it's going to be a function of every exogenous variable in the problem. Well, which is typically how we do this. Well, we've got a couple of exogenous variables, and I may need to add a little bit of information here, but let's just go with what we know so far. So here we have D star as a function of D and Q. And we take the first order condition of the second problem, we get something similar. Okay, so nothing looks yet like it's a best response to a best response, but let's notice these, the choice variables in the other problems. So here we have D and R, and D of course is going to appear in every term just like it always does, but what about R? This choice variable actually does appear up here. So what we saw before with principal agent was that the solution to one player's problem was inside the other player's problem as part of their objective function. So do we see that in both problems? So here we have D as a choice variable, and down here we've got dr. Could this be D star R? And how do we interpret this? Well, the way we interpret this is this player is choosing their choice variable D in order to at least somewhat influence the behavior of the other player, or they know that their choice of D is going to influence the other player's best response. And same here, this player's choice of R is going to influence D, and there's this back and forth. So if we look at the solutions, what we're going to find is we're going to find something like this, where the choice of D needs to be in response to R, and the choice of R needs to be in response to D. And that's going to represent some kind of Nash equilibrium. So this is how you identify Nash equilibrium in a problem. It's going to have some format where there's this, it's actually symmetric if you notice, like R is a function of D, well, D is a function of R. These are just flipped according to whose choice variable matters. And that's how game theory problems look when you set them up inside problems. And of course, if it doesn't meet either of these two criteria, it's neither game theory or principal agent. So let's look at another example. And you've probably figured out by now the fastest way of thinking about this is looking at the two choice variables and identifying them in each other's problems and seeing what type of variable they are. So J, J appears in this player's problem over here. Q appears in this player's problem over here. This is exogenous. So if this is principal agent, this is going to be the principal because their choice variable appears in the other player's problem as a exogenous variable. Now the question is the solution to this top problem, J star, is that a function of Q, of the other player's choice variable? So does it appear in the objective function? And as a matter of fact, yes it does. That means this J is going to be the optimized value for J from the other player's problem. In other words, this function is derived from the solution to this optimization problem. That's principal agent. So this is in fact a principal agent problem. Let's look at another problem. All right, let's check and see if this is either principal agent or game theory. So we've got our two choice variables, H and Z. H does not actually appear in this problem, so this one actually cannot be principal agent or game theory because this choice variable does not appear in the other problem. But let's see if we can make a small adjustment to these models to make it into a game theory problem, just to challenge ourselves. So Z actually does appear. Z does appear up here. So we can assume this Z is Z star as a function of H. It's derived from the solution to this optimization problem. So the question is, can we stick H inside this function somewhere as a function of Z? And we could do that. We could do that simply by making H. So now this is H star as a function of Z. So this is going to be best response to a best response sort of situation. And that's going to represent a Nash equilibrium solution to a game theory problem. So I hope you have a sense for principal agent and game theory problems and the way they appear when you look at functions.